Okay, so what I'd like to do in this video then is show you sort of some overall operating principles of the speed-of-light apparatus. And so I have everything in close proximity once again. Transmitter receiver right here, Fresnel lens, and the retroreflecting mirror. And I would say there's probably about a 2-foot distance between the transmitter and the reflector over there. So that's a 4-foot total flight path for the light to go to make it back over here. Okay, so about 4 feet. So if I go back and look at the oscilloscope now, what we have are those 2 pulses coming out of the A and the B outputs, as mentioned. And let's see if we can maybe even take a quick measurement here to see how it's working. Okay, so we see the 2 pulses on here. They don't look very separated, but what we'll do is we'll go on the oscilloscope here and get the cursors going here, which are helpful for measuring. And I'll choose cursor X1, cursor X1 to be over here on that B pulse coming out. So that vertical line that I just put on there, I tried to center right over the yellow pulse, which represents again the light that is just coming out of the transmitter. And additionally, what I'll do then is I'll turn on the next cursor, cursor 2, and I will center that over on the green pulse, which is, of course, as we know, is a pulse coming back from traveling out the 4 feet, 2 feet out, 2 feet back. So the pulses do look like they're delayed just a tad bit, and I'm getting a delta X of about 4.6 nanoseconds. Okay, so what does that mean? Well, I know that light travels about 1 foot every nanosecond. Okay, and so as I mentioned here, in the setup that we see here, I think just sort of estimating by eye, there appears to be about 2, or looks like a little more than 2 feet between this transmitter and this retroreflecting mirror. So say a little more than 2 feet. And so if it takes about 2 nanoseconds to go out at about 1 foot per nanosecond and 2 nanoseconds to come back, well, that's about 4 nanoseconds. And lucky for us, that's almost exactly what I'm getting here. I'm getting about 4.6 nanoseconds on the return. Okay, so just to make the point, so I think it's working okay is my first point here. So what I'll do now is I'm going to take that retroreflecting mirror and I'll pull it back maybe, I don't know, another 4 feet or so. So I'm going to put it way back over here on the table. And of course, if you're actually operating this, you always have to be a bit careful aligning the mirror to make sure that, so there's the mirror back on the table now, but I'm going to sweep back to the oscilloscope because as you operate this thing, as you move the mirror, you have to make sure that it's aimed so you're getting a nice return. So I'm going to go over and move the mirror now, and I'm going to keep my eye on that green pulse there to sort of to maximize that just as much as I can. So see there, it's sort of going away as I move it. There it's sort of back, and maybe I'll tilt it side to side a bit. So something like that I think is about maximum for it. So I'll just leave it there. So see, indeed, again, I am getting a return. And the other thing I can do over here is just to convince myself that it's actually light coming back. You always have to make sure when you do these experiments that the signal is you think what it is what I'm going to do is I'm going to take this piece of paper right here. I have this piece of paper right here, and I'm going to sort of hold it over in front of that mirror over there just to make sure that this green pulse is actually being generated by light coming off of that mirror over there. So I'll just do it in a couple places. Of course, so what I'm going to do now is I'll put the piece of paper right in front of the transmitter, and of course see the green goes away. Okay, there still is a little bit there, maybe some internal electronics, but clearly there's a light effect. Then I'll put it just on the back side of the Fresnel lens. Goes away once again. Okay, now I'm going to walk over and I'm going to put it right in front of that retroreflecting mirror, and of course it goes away. So in front of the mirror, pulling it out, putting it in, putting it out. So indeed, it does appear as if that green pulse is coming from light that's reflecting off of that far away retroreflecting mirror and back into the receiver. And so let's go back to the cursors now and see if we can nail this down, because it does appear as if this peak here has shifted over to the right a little bit, indicating that light is actually traveling. There's a bit more time delay in that return signal as light travels across the room. Not very far, but still. So maybe right about there is where the peak would be. And of course, if I do that now, the oscilloscope is telling me there's about an 11.8 nanosecond delay between these 2 cursors that I have on the oscilloscope, about 11 nanoseconds. So I'm just sort of looking back then at the whole thing. Does that make about some sense to me? I won't do any calculations now. That's sort of what your job will be when we run the lab. So okay, well there's the detector emitter right here, and there's that retro mirror over there. So I'm just sort of looking at it here, and it looks like it's probably about, looks like it might be about 6 feet between this and that mirror over there. So 6 feet or so, that's about 6 nanoseconds one way out. And again, the delta X I'm getting at the moment here is about 11.8 nanoseconds. That's close to 12. So it does seem like it's about working a 12-foot total travel time, 1 foot per nanosecond. I'm getting about 12 nanoseconds over there on the oscilloscope. So that's sort of the idea there, is that by increasing the delay, or the time, increasing the distance between that retroreflecting mirror and the receiver, we can change the receipt time of the return pulse relative to the transmitted pulse. In other words, here's the transmitted pulse, there's a return pulse, and so we can just generate for ourselves a bunch of distance versus time data points, and that's where the speed of light will come from. So in the data videos that follow, what essentially I'm going to do is show you the retroreflector at different distances from the transmitter. That'll be one shot you see, and in the very next shot you'll get a picture of what the oscilloscope looks like, and all that will be up for your own interpretation to take your own data. Okay, there we go.